Hey everyone. Today we're going to explore the fascinating relationship between Cloud Run and native serving. Understanding this connection is crucial for anyone working with modern containerized applications. Let's start by looking at these two technologies separately. On the left, we have Cloud Run. This is Google Cloud's managed service for running containerized applications. On the right, we have native serving, an open source project that provides serverless capabilities on Kubernetes. Now, here's where it gets interesting. Cloud Run isn't built from scratch. It's actually built on top of native serving. Think of native as the foundation and Cloud Run as Google's managed wrapper around it. Here's a better way to visualize their relationship. Native serving provides the foundational serverless capabilities, while Cloud Run adds Google's managed services, monitoring, and enterprise features on top. One of the most powerful aspects of this relationship is API compatibility. Because Cloud Run is built on native, the underlying APIs are very similar. This means you can often move your applications between Cloud Run and native with minimal changes. This relationship provides several key benefits. First, you avoid vendor lock-in because you're not tied to Google's proprietary technology. Second, you have the flexibility to choose between managed and self-hosted solutions. Third, you get a consistent development experience across platforms. And finally, you can easily migrate between different environments as your needs change. Here's the key takeaway to remember. Cloud Run is built on native serving, which gives you incredible flexibility and portability. You're not just learning one proprietary service, you're learning a technology stack that works across multiple platforms and environments. So you might be wondering, if Cloud Run is built on native serving, why would you choose to use native serving directly instead of the managed Cloud Run service? There are two main reasons why you might choose native serving over Cloud Run: portability and regulatory needs. The first reason is avoiding vendor lock-in. With Cloud Run, you're tied to Google Cloud's infrastructure, but with native serving, you have the freedom to run your applications on any Kubernetes cluster, whether it's on AWS, Azure, on-premises, or anywhere else. The second reason involves regulatory and regional requirements. Some organizations need to comply with data sovereignty laws, or they operate in regions where Google Cloud isn't available or is restricted by government regulations. With native serving, you can deploy the same application across different Kubernetes clusters, whether they're running on Amazon EKS, Azure AKS, or your own on-premises infrastructure. This gives you unprecedented flexibility and control over where your applications run. Here's the key takeaway. Native serving offers portability and control beyond Google Cloud's reach. While Cloud Run provides convenience and managed services, native serving gives you the freedom to run your serverless applications anywhere Kubernetes can run. Now let's talk about Kubernetes. At its core, Kubernetes is a container orchestrator. But what does that actually mean? A container orchestrator is a system that automates the deployment, scaling, and management of your application containers. Kubernetes makes sure your containers are running on the right machines. It distributes your applications across multiple nodes in your cluster. It also ensures that network traffic can reach your containers, routing requests to the appropriate applications wherever they're running. Think of Kubernetes as the conductor of an orchestra. Just like a conductor coordinates all the instruments to play together harmoniously, Kubernetes coordinates all your containers to work together seamlessly. Here's the key takeaway. Kubernetes manages and automates container deployments. It handles deployment across multiple machines, automatically scales your applications, manages network routing, and ensures your containers stay healthy and running. The Kubernetes API server is the beating heart of every Kubernetes cluster. Think of it as the central command center that coordinates everything happening in your cluster. The API server sits at the center of your Kubernetes cluster, acting as the single point of entry for all operations. Every request, whether from kubectl commands, other cluster components, or applications, must go through the API server. The API server performs three critical functions for every request. First, authentication asks, "Who are you?" verifying the identity of the requester using certificates, tokens, or other credentials. Next comes authorization, which asks, what can you do? The API server checks if the authenticated user has permission to perform the requested action on the specified resource. Finally, validation asks, is it valid? The API server checks that the request follows the correct format and that the resource configuration makes sense according to Kubernetes rules. Now, here's something crucial. The API server is the only component in your entire Kubernetes cluster that talks directly to the cluster database, called etcd. etcd stores all the information about your Kubernetes resources, pods, services, deployments, secrets, and everything else. The API server reads from and writes to etcd to maintain the current state of your cluster. To help you understand this better, think of the API server like an airport control tower. Just as all aircraft must communicate with the control tower before taking off or landing, all Kubernetes operations must go through the API server. The control tower manages all incoming and outgoing traffic, ensures safety protocols are followed, and maintains communication with the airport database about flight schedules and runway availability. This analogy perfectly captures how the API server works. It's the central control point that manages all cluster operations, enforces security and validation rules, and maintains the authoritative record of your cluster's state. Remember this key takeaway. The API server is the central control point for Kubernetes. It handles authentication, authorization, and validation. It's the only component that talks directly to etcd, and all cluster operations must go through it. Kubernetes controllers are like diligent workers, constantly monitoring your cluster. Think of them as supervisors who never sleep, always checking that everything is running exactly as you specified. Controllers work by constantly comparing two things: the desired state that you've defined and the actual current state of your cluster. The controller continuously monitors both states. In this example, you want 3 instances of your application running, but only 2 are currently active. When the controller detects a difference, it immediately takes action to reconcile the states. Since we need 3 instances, but only have 2, the controller will create a 3rd instance. This process never stops. Controllers run in a continuous loop. They observe the current state, compare it with the desired state, and take action when needed. This ensures your cluster always matches your configuration. The key takeaway is that controllers ensure your cluster matches your desired configuration through continuous monitoring and automatic reconciliation. They're the guardians that keep your Kubernetes cluster running exactly as you intended. In Kubernetes, the smallest deployable unit is called a pod. Understanding pods is crucial because they form the foundation of how applications run in Kubernetes clusters. A pod represents a single instance of a running process in your Kubernetes cluster. Think of it as the basic building block that wraps around your application containers. The simplest case is a pod containing just one container. This is the most common scenario where your application runs in a single container within the pod wrapper. However, a pod can also contain multiple containers that work closely together. These containers are tightly coupled and share the same resources, like network and storage. To better understand this concept, let's use a helpful analogy. Think of a pod as a single apartment in a building. The building represents your Kubernetes cluster, and each apartment is a pod that can house one or more residents, which are your containers. Just like residents in an apartment share utilities and space, containers in a pod share important resources. Containers within the same pod share key resources. They share the same network interface, meaning they can communicate with each other using localhost. They also share storage volumes, allowing them to exchange files and data easily. Now let's highlight the key takeaway from understanding pods. The key takeaway is that pods are the basic building blocks for deploying applications in Kubernetes. Every application you run in Kubernetes, whether it's a simple web server or a complex microservice, starts with creating pods. Remember this fundamental concept. A pod is the smallest deployable unit in Kubernetes. Understanding pods is essential for working effectively with Kubernetes applications. Want to learn Kubernetes but worried about breaking something important? Minikube is your perfect solution. It's a tool that creates a complete Kubernetes cluster right on your local machine. Unlike a production Kubernetes cluster that runs on multiple servers in the cloud, Minikube creates a single node cluster that runs entirely on your laptop or desktop computer. Think of Minikube as your personal Kubernetes sandbox. Just like a playground where children can experiment and learn safely, Minikube gives you a safe environment to try Kubernetes features without any risk. Minikube has several key features that make it perfect for learning. First, it's incredibly easy to set up. Just one command gets you a running Kubernetes cluster. Second, it runs everything locally on your machine, so you don't need internet access or cloud accounts to practice Kubernetes. Third, and perhaps most importantly, you can easily reset everything if something goes wrong. Made a mistake? Just delete and recreate your cluster in seconds. Here's how simple the Minikube workflow is. You start your cluster, experiment with Kubernetes features, and if anything breaks, you simply reset and start fresh. The key takeaway is that Minikube removes all the barriers to learning Kubernetes. You don't need expensive cloud resources, complex setups, or fear of breaking production systems. It's your personal Kubernetes playground where you can learn, experiment, and grow your skills safely. When you deploy services with native serving, there's a critical component that often gets overlooked: the HTTP load balancer. Without it, your services would be unreachable from the outside world. Imagine you have multiple service instances running in your cluster, but incoming HTTP requests don't know which instance to reach. They're essentially lost without proper direction. This is where the HTTP load balancer comes to the rescue. In native serving, we commonly use Courier as our load balancer. Think of it as the front door to your services. The load balancer acts as a smart router. When HTTP requests arrive, it examines them and decides which service instance should handle each request based on factors like current load and availability. Think of the load balancer like a traffic cop at a busy intersection. Just as a traffic cop directs cars to the right lanes to prevent congestion, the load balancer directs HTTP requests to the right service instances. Without a load balancer, your native services would be like a building with no front desk. Visitors wouldn't know which floor or room to go to. The load balancer ensures every request finds its way to the right destination. Here's the key takeaway. A load balancer is absolutely essential for routing traffic to your native services. It's not optional. It's the critical component that makes your services accessible to the outside world.